Okay, everyone. Good afternoon. I should start. So, in the last lecture, we have a brief start with probabilistic graphic models. So, as we discussed, probabilistic graphic models is a big branch. Basically, it uses the graph theory to represent the probabilistic model and facilitates your inference and analysis of probabilistic models. So, roughly speaking, probabilistic graphic models can be it consists of two types of models. First one is called Bayesian networks. The second is called Markov random field. But there's some kind of hybrid graph in that. It's not. It's just some frontier research. But classical way we consider two types of graphs. One is directed graphs, so they are called Bayesian networks. The other is called like Markov random field. They're all about like undirected graphs. So we start with the Bayesian networks. So the construction of Bayesian networks is motivated by the expansion of the base group. So basically, whenever we have like two random variables, x1 and x2, remember x1 and x2 can both be vectors, doesn't matter. So the condition distribution of x2 given x1 according to base rule can be written as a joint probability of x1 and x2 divided by the marginal probability of x1, right? So we can like if we multiply this denominator to the left hand side, we have the joint probability of x1 and x2 equals to the marginal probability of x1 and the probability of p of x2 condition on x1, right? So we can further expand to like an arbitrary number of the random variables, say n random variables now. By using like base rule to expand it, we can represent it as a product as a p of x1 multiply with P of x2 condition on x1, right? P of x3 condition on x1, x2. You just continue until P of xn given x1, x2 to xn minus 1, right? Verify this is pretty straightforward, right? Because we will multiply the first two, like P of x1, P of x2 given x1, we get marginal drawn probability of x1, x2, right? Then we multiply again with this P of x3 given x1, x2, you get drawn probability of x1, x2, x3, right? You can just do this continuously until you multiply the last term, you end up with this. So let us consider a specific case. Like we only consider 3 random variables in our probabilistic network, A, B, C, right? So we can factorize our joint probability according to Bayes rule as like first probability of A, and then P of B given A, right? And P of C given A and B, right? This is a standard application of Bayes rule. So the natural question is that can we use a graph to represent their joint probability? Right? So intuitively, like each random variable can be represented by one node in the graph, right? So suppose we have like 3 random variables, we can draw 3 nodes in our graph. There was A, B, and C, right? And the issue is that how can we express their dependencies? So I mean the links. How should we know like which nodes are connected, which nodes are not connected, right? So we can observe their dependency from the factorization of their joint probability, right? So you can say like basically your joint probability can be factorized the product of the conditional probabilities, right? And like for this marginal probability, you can consider a special type of conditional probability where you condition on nothing, right? So for any like conditional probability, we know that the variable and the variables are conditioned on are dependent, right? Because I have to, if I want to give this a probability, I must know the value of the variables which are conditioned on, and also the value of the variable we describe, right? So obviously, in this conditional probability P of B given A, we know A and B has some dependency, right? So we can consider A as the parent of B, because given A, we got B, right? So we can issue a link from A to B. Right? So let's go back to this term, right? A special conditional probability means that a condition on nothing. Means that, okay, I just get A. I do not need to look at the values of other variables, right? So that just means, okay, I do not have any incoming link. No one else is going to issue a link to me. Okay. So, and then for this P of B given A, we know A links to B, right? And then the remaining conditional probability is P of C given A and B. So here we see that the conditional parts consist of the A and B, 2 random variables, right? They're both safe, depends on both of them. So we consider A and B are both parents of C. So that means we issue a link from A to C and from B to C. So this is a Bayesian network. So basically, just to express is just use some graph, directed graph to express the dependency reflected in the factorization of your joint probability. Yeah, here's the just a more nice looking figure for this. So, so here's the common rule to draw your Bayesian network for like any probabilistic models. So basically, given the joint probability of your models, like you consider you have like n random variables, then for each each random variable, we represent it as one graph node or vertex. And then for each condition distribution in the drawn probability, so it can be in general written as a P of A given B1 to Bn. And then we add an edge from each Bi in its conditional parts to A. So the random variables in the conditional parts are represented as the parents of A. If there are no condition parts, like marginal probability, then the node has no parents. That means there are no incoming edges to that node. That's the rule. Yeah, that's the rule. So we can look at a more complex example, right? So we have like 7 random variables, and this is our joint probability, which can be factorized in this way. And how can we construct our Bayesian network representation? We just look at each term. So first, P of x1 is conditioned on nothing. Means that, okay, I do not have any edge which connects to me, right? So you have Px1, right? No incoming edge. And P of x2 conditioned on nothing, so no incoming edge. P of x2, and P of x3, no incoming edge. And the fourth term is P of x4, conditioned on x1 to 3. So we have like x4 has 3 parents, right? That means for x4, you need to connect each of its parents to x4. So x1, x2, and x3. Right? And the next term, P of x5, given x1, x3. So it's conditional on x1, x3. That means x1, x3 are parents of x5, right? So we need to connect x1 and x3 to x5. And continue, P of x6 given x4. So x6 only has one parent. So here x6. So just connect x4 to x6. And finally, P of x7 given x4 and x5, 2 parents, x4 and x5, is to connect them to x7. Right? So reversely, if you are given this graph, right? If you are given this graph, given this Bayesian network, you have any question? Okay. So if you are given this graph, you can immediately write down the joint probability, right? The product, right? It's pretty straightforward. P of x1, because I do not see any incoming edge. P of x2, P of x3, and then look at x4. Oh, it's given x1, x2, x3 because it has like 3 parents, right? P of x5, x1, x5, given x1, x3, and blah blah until I write down a conditional probability for the last node, right? Any question? I think it's quite intuitive, right? So we name this representation as a Bayesian network. So something you keep in mind, Bayesian network is directed graph, right? Because it indicates the relationship, like your parents and you. So this is kind of like a one single directional relationship, like it's not symmetric. And second thing, should be aware is a cyclic graph. That means in this graph you cannot have a cycle. Cycle means that, for example, I have like x1, x4, then x4, x2, and x2, x1. This is not allowed. And why? Why can't we have a directed acyclic graph for Bayesian network?
It just generates one probability of one because one is pre-conditioned to the other one and the other one, and the other one value like both of them.
Yeah, I think you catch the meaning. So let me reorganize max where you have set, right? So basically, this network, I mean, the factorization of the joint probability not only represents how you calculate the joint probability, it also represents the way you sample all the random variables, right? So imagine like you have like 7 random variables. Then according to this factorization structure, the first sample x1, right? Or let me explain it in front of the graph, right? I first sample x1, then I sample x2, then I sample x3, right? And then given x1, x2, and x3, I sample x4. And given x1 and x3, I sample x5. Given x4, x5, I sample x7, and given x4, I sample x6, right? So this is a sequential sampling procedure. All the variables which have already been sampled cannot be sampled again. They can only be used to sample a new variable. If you allow some cycling structure, it means that, okay, this time I sample x1, right? And I condition x1, I sample a set of new variables, but at some future time point, given those samples, given new variables, I sample x1 again. This causes a cycle. And this is not a valid sampling procedure. Right? So remember, if you use like a Bayes rule, you're also sampling a sequence of the random variable once. Right? You cannot sample n of them twice. But if you allow the cycles in your graph, that means okay, you're sampling twice.
So does that mean like P of x1 given x1 is not valid because it's self-proof to itself?
Yeah, of course. Any question at this point? And in essence, that means when you use like Bayes rule to expand your joint probability, any variable like cannot appear in the cannot appear in front of the conditional part twice. And you cannot like have something like px1 given something and times px1 given another thing. It's not allowed if you use Bayes rule to expand the joint probability. Does it make sense? Hopefully you are not confusing at this point. Because this rule is exactly the property comes from the Bayes rule. If you use any like expansion according to Bayes rule, you'll see that one variable can only appear in front of conditional once, but it can appear in conditional parts like many times, but it can only appear in front of the conditional part once. Okay. Okay, let us look at some example, practical example for Bayesian networks. Right? So polynomial regression. So what is polynomial regression? If you still like have some impression, basically means okay, I have a scalar feature x, right, and I choose an order polynomial. So I have say I take order 3, then I have 3 features x to the power of 0, 4 to the power of 2, and to the power of 3, right? So I use this vector as my transform feature vector and construct a linear regression model. So basically, we have like 2 random variables. First is feature weight vector, and second are the observation from the trained data set. So here the bolded t is a vector. Suppose we have like n labels, right? So t is like an n-dimensional vector. So we can factorize this joint probability as a prior of the weight vector, then multiply with the likelihood. Given the prior, given the weight vector, we usually assume that those labels are independent, right? So our likelihood can be written as a product over each likelihood P of t and given W. Right? So how do we represent in terms of the Bayesian network? So first we draw a circle that's null, right? Represent W. And then given W, we sample each of the labels, so T1 to Tn. So each circle, each node represents a particular label. That's it. Any question at this point? But issue is that sometimes we need like more detailed information about our model, right? So, for example, who determines our prior, right? We know that we usually use Gaussian prior to as a prior for our weight vector, right? The Gaussian prior is usually determined by the variance parameter alpha. And also, we use the Gaussian likelihood to model the probability that how given the weight vector and the input feature to sample Tn. Because we use Gaussian likelihood, we also need to determine the variance sigma squared. Right? So we can say, actually we have like two hyperparameters, alpha and sigma squared. Right? And if we use empirical Bayes framework, we do not care about the distribution, we just want to do a point estimation on that. So usually we call it hyperparameter. And also, the random variables not only include the weight vector W and the label Tns, but also include the observation, input observations, the input features of variables, whatever, Xn. The issue is that we do not care about the observations. We do not model how we sample, how we generate the observations. Then we want to show all those information in the Bayesian network. What should we do? Another issue is that like we have like n samples, right? So now, okay, for each particular sample, like your Bayesian network structure is kind of similar, but I do not want to replicate the structure like for 100 times. So do we have like a more succinct representation? So here's the way. I mean, the custom we show all those information in Bayesian network. So first, we use small solid nodes to represent those deterministic parameters. So what are the deterministic parameters? The alpha and the sigma squared, right? Because we want to have some point estimation, that would be sufficient. So we draw alpha and the sigma squared as like a small solid nodes. And also, for some observations, we are not interested to model them. We can also draw them as like a small solid nodes. That's where each input feature Xn are represented. And then we use big empty node to represent those latent variables. That is the weight vector W and each label Tn. And more important, to avoid repeatedly drawing the same structure, we introduce a plate. If we put a plate outside some structure, and then I put a label n here, just means I replicate the structure for n times. Because each of these Xn, Tn will share the same kind of structure. We do not need to repeat drawing this like 100 times or even 1,000 times. Okay? So, in the training data, because the outputs, that means those labels or continuous responses can be observed, and then we shade the observed latent variables to show that it is observed. So, because training data, each output Tn observed, so I just shade that. So, the only things unknown are the only random variables, latent random unknown, are about the weight vector, and we want to estimate the posterior of the weight vector. Right. Any questions so far? There's just some custom to draw the graphic models and to make your graphic model more professional, more elegant. Okay. Here are some notes for when you construct Bayesian networks. You should be aware. So first, the network structure is determined by the factorization of the joint probability. So that means like different factorization leads to different structures. Right? Even they express the same joint probability. If you choose different factorization structures, you may end up with different network structures. For example, our three random variables probabilistic model A, B, and C. Right? So here we do not make any assumption. We just use a full Bayes rule to factorize it. The first one is I first multiply with P of A, and then P of B condition on A, and P of C condition A and B, right? And the second one is like start with P of B, and then P of C condition on B, and P of A condition on B and C. So the question is, are the corresponding Bayesian networks the same? The answer is always no, right? Although, I mean, from the joint probability perspective, they are equivalent, but because the choice of the factorization structure, you end up with different Bayesian networks. So, how to design a factorization of your joint probability is actually the key of the probabilistic model. So if you do not have any assumption, you do not have any belief or knowledge about how to factorize it, you can use the full Bayes rule to factorize it. That means your model does not contain any special information. In other words, it might be like useless. And if you do not incorporate any special structure or assumption about factorization, use full Bayes rule, right, to factorize your joint distribution, you end up with a fully connected Bayesian network. We can verify this, right? So suppose this is x1, and the first you multiply in P of x1, right? And then you multiply in P of x2 given x1. And for the third variable, x3, you multiply P of x3 given x1, x2. Right? So you have to connect the previous two nodes to x3. And for x4, because you have no extra assumption, you need to use P of x4 given x1, 2, 3, right? So it means all the previous nodes must connect to x4 as well. So you see, it's always fully connected. Right? Any question? Anyone? You are comfortable?
I follow the Bayesian network thus far. I wonder if we can see an application of it either in code or by hand.
Yeah, there are like numerous applications.
Right, but would it be possible for you to walk us through one in class, or is that something we should just go seek out outside class?
Basically, we're going to see a few detailed models after we have looked into the basic ideas and framework for the Bayesian networks. You'll see like nearly all kinds of probabilistic models are Bayesian networks, so I'll mark a random fields. Does it make sense to you, or you want to see a practical example right now?
I think I would like to see examples at some point, or if you would like, or if it's better for us to just stay to the mathematical models instead of in class, and then have external reading for following fun examples.
Yeah, you will see the example right now.
Okay.
Okay. So if you do not introduce any assumptions, use like full Bayesian rule to expand your joint probability, you will not fully connected network, right? But actually, fully connected network is not what you want. So basically, in practice, the Bayesian network is always sparse. That means many edges are just cancelled. The reason is that we put extra assumption on that, and that the assumption is based on our own understanding of the problem you want to solve. Right? So that's here. We nearly always use domain knowledge to simplify the joint probability, which can be reflected by a network structure. And it's fully connected network structure is not good. You want something like simplified structure, and this simplification is called conditional independence. So here we look at some practical model. It's called a linear Gaussian model. So assuming that we have like big N variables, x1 to xn, right? So all we know is that we follow some multivariate Gaussian distribution without any assumption. So if I want to estimate the parameters for this multivariate Gaussian distribution, how many parameters do we need? So multivariate Gaussian distribution is determined by what? By a mean vector and a covariance matrix, right? So basically, you have like n by 1 vector. So your mean vector will be n by 1, and the covariance is n by n, right? So if we do not put any assumption of the relationship between those random variables, we need to estimate like n squared parameters, right? And you can represent it as like Bayesian networks. It will be like fully connected. As we mentioned, this is not good. So now let us choose some Bayesian network. We choose this chain to represent our practical models, to model this set of multivariate Gaussian random variables. So we start with x1 and then connect x1 to x2 and connect x2 to x3. So remember, x3 only has one parent x2. Right? And it does not have a parent x1. And similarly, x4 only has one parent x3, and he is not connected from x1 to x2. So that's where we simplify the structure. And then we define our conditional probability regarding each node, right? So ith node given its parent as a Gaussian distribution with the mean to be a linear combination of its parent plus the intercept and with the variance bi. So here the weight wij and bi intercept bi and the covariance the variance bi are just parameters. So now if we choose this linear structure, someone asks how many parameters do we need to estimate? Because for each, yeah, 3. For each particular conditional distribution, right, we need to, it only has one parent, right? So this is actually just one scalar weight, and then plus an intercept, and then plus variance parameter, so 3, right? So I have like n random variables, you have like n conditional components, so it's just 3n. So now we reduce the number of parameters to proportional to n. That's what the benefit a simplified structure can give us. And also, this is how you design your practical model. If you do not have any knowledge and beliefs on models, then you use like some kind of totally uninformed model that is fully connected to Bayesian networks, right? But now, if you have some knowledge, you believe, okay, each x2 is only depends on x1, x3 only depends on x2, but does not depend on x1. So it greatly simplifies the structure and also greatly reduce the number of parameters vastly. But as to how you come out with the structure, it depends on yourself. It is determined by you. For example, I can choose another structure. It's not necessary for me to choose a chain structure. I can choose a tree structure. I can choose a something like this one, x1, x2, and then x3, and x4, and continue, right? So you can choose whatever structure you want, but this must reflect your belief, your choice of your model. So in general, simplification of the Bayes rule, or in other words, simplification of the fully connected Bayesian network, reflects our ideas, tricks, and knowledge in probabilistic modeling. And mathematically speaking, how is the simplification reflected? This is called conditional independence. So, to illustrate what is conditional independence, let us do based on the 3 random variables model, ABC, right? So we say A is conditional independent B given C if this is the probability of A conditional B and C is probability of A given C. Then we say A is conditional independent B is independent B conditional C. So this is another notes to represent conditional independence. So I just want to check your memory about Bayes rule. Why this means A and B are conditionally independent on C. Why? So first, conditional independence has nothing different with like independent. So if you like just like cover C, right? It just means like P of A given B equals to BA, means that conditional probability is the marginal probability. Then that means like A is independent of B. If you say okay, something is conditional independent given a third variable, you just add some third variable in the conditional part. And this is equivalent to say the probability, the joint probability of A and B equals to a probability of A multiplying P of B. This can be easily verified from the Bayes rule. So here's the same thing, right? If you just wipe out C, you can see P of A given B, A, they're the same. So let us look at a few like basic structure because we want to answer any query like how about one set of random variable are independent to another set of random variable given a third set of random variable. We want us to be highly efficient and to be able to answer this question on given Bayesian network, no matter how complex this network structure is. So to answer this question, we'll start with like a basic structure, some local structure of your Bayesian network, and see how we extend the rule to like the global network structure. So we can first look at this structure. So if we use the Bayes rule to expand this joint probability, we can start with C, right? We start with C and then multiply with P of B conditional C, and multiply P of A given B and C. But according to the structure, we can represent this joint probability according to the structure. It's P of C, and P of C given B, and P of B given C, and P of A given C, right? So now we can see actually the third term for the two factorizations are the same. We can see that the network structure is simplified by removing one edge, right? And when we go back to look at the factorization, we see these two terms are the same. It basically means where A and B are conditional independent given C, right? So see the correspondence between the structure and the conditional independence, right? Because in the structure, this is not a fully connected structure. We miss one edge. If we want to have a fully connected structure, we have to add one edge, right? So now in this structure, I do not have this edge. And what's the result and what's the consequence when I write down the factorization of job probability? I see this term is this term, which show you that A and B are conditional independent given C. So in practice, how do we design a Bayesian network? Okay. So when you are given a network, if you want to invest all kinds of properties, you should investigate conditional independence. But when human beings design a Bayesian network, we're not going to list all kinds of conditional independence. That's too strange. So more intuitive, more natural way to design a model is to consider a sampling procedure. For example, I want to first consider how I sample x1, right? So I believe that x1 is sampled from some prior. It does not need to condition on whatever other random variables. And then given x1, I believe we should sample x2 and x3. And given x2 and x3, I believe I should sample x4. So when you work out this sampling procedure, you can just intuitively write down or draw the Bayesian network. Right? So you see the difference, right? The design procedure is just to work out one single sampling procedure to draw the instance of all the random variables we're interested in. But when you do analysis, when you do the retrospective analysis, we need to investigate all kinds of conditional independence. Like given x1, whether x2 and x3 are independent. Given x1 and x4, whether x2 and x3 are independent. So sometimes you might even not realize some kind of particular conditional independence because you only work out one simple or one intuitive sampling procedure. And when you draw down, we will jot down your probabilistic boundary models. Then we look back, we find okay, there might be some interesting conditional independence. So see the difference, right? The difference when you design your Bayesian network and the difference when you analyze some given network. So this is a design. So when you are given a network, say like a network which contains like thousands or even hundreds of thousands of variables, very complicated structure, how do we analyze them? We want to ask a question. Given arbitrary non-intersecting sets of nodes A, B, and C, this means A, B, C are three groups of random variables, and they are not overlapping with each other. Then how do we tell whether given the set of random variables in C, A and B are conditionally independent? This is the key strategy to probe our Bayesian network, to study what's the property this Bayesian network reflects, right? But the first question is how can we justify this, right? How can we tell whether they are conditionally independent or not? Right? This is actually not very easy to answer. Why? Because like imagine you have like 1,000 random variables and a very complicated product of your drawn distribution, and these are just subsets of the random variables. So A might be like 2 random variables, B another 2, and C another 3, but you have 1,000 random variables. If you want to use the original concept to prove that, you need to marginalize a lot of other random variables. 0 is infeasible. Then the question is that, can we use the structure of the graph to answer this question very efficiently? So we're going to introduce this fundamental algorithm called deception, and sometimes this is called baseball algorithm. Deception is based on like 3 basic structures, local structures, and we're gonna like use these local structures to give a conclusion whether like there exists some possible dependency, conditional dependency. If all possible conditional dependencies are removed, are excluded, then we can safely conclude they are conditional independent. So the first basic structure is called tail-to-tail. So again, we consider like A, B, and C. So A and B and C here are just three variables. A, B, C. It's not three sets of variables, just three variables. And why it's called tail-to-tail? Because we look at where the edges meet at this node that are conditioned on. So you see, because this edge starts off, the both edges start off from the conditional node C. So they are tails. Right? This is called tail-to-tail. And given the tail-to-tail structure, what we can tell is that A and B, if conditioned on nothing, they are not independent. Usually they are dependent. But if they are conditioned on C, given C is observed, then A and B are independent. Do you see the difference? So if we do not assume any variable are conditioned here, A and B are generally not independent. But if we assume C is observed here, A and B must be independent to each other. And we can verify this use Bayesian theorem. So according to this structure, the joint probability for A, B, C can be written as P of C, right? Start from the parents. And P of A given C, and P of B given C, right? And if we look at whether A and B are independent to each other marginally, we need to look at the joint probability of A and B, right? So if they are independent to each other, they should be able to factorize as P of A multiplying with P of B, right? Now we need to verify with this joint distribution, right? So we know P of A and B is equal to the joint probability marginalized with C marginalized out, right? So if we use the factorization structure reflected from this network, we have to integrate out C in this product, right? This is just copy from here. So now we can see, will we be able to factorize this integral into two terms? I mean, in general, probably in special cases it's doable, right? But in general, can we break this integral like some term like HA and HB, right? HA only contains A, HB only contains B. Is it possible? No, right? Why? Because you see, C connects A and B. So this product share with C, right? And now you integrate over C. That means you want to remove C. So the cost is that when you remove C, you just couple these two terms, right? That means A and B are always twisted. They're coupled together in one term. And in general, we can now conclude that and it can be factorized as a term which only contains A and another term which only contains B. Everyone's comfortable, right? Because you guys don't respond, I thought it's pretty easy. Yeah, it's pretty straightforward. So, and then we can say this conclusion is correct, right? And now let's look at whether A and B are independent given C or conditioned on C, right? So to look at this, we can check the conditional probability A and B, P of A and B given C, right? We want to see whether it can be written as P of A given C and P of B given C, right? If this holds, then they are conditionally independent, right? And then we can just take a look, right? So here, P of A and B given C is just P A, B, C, right? The drawn probability of 3 random variables divided by the marginal distribution of C. So now just substitute this factorization for the drawn probability. Just copy here. So I have the P of C times P of A given C times P of B given C and divided by P of C. So what can we observe? What can we observe? Yeah, we just cancel P of C in both denominator and numerator. You have this factorization form. Right? Consistent with this, all we can conclude that given C and B are independent. So for the first basic structure, for the tail-to-tail structure, we can safely conclude that A and B are conditional independent given C. Well, if C is not observed, A and B are usually not independent, right? So you can imagine that it's just like you have a ball, right? So this is a pass, connect A and B. You have the ball, you start with A and you just roll it, right? You just roll it, and if this pass is not blocked, it just safely goes to B. If C is not observed, means that the pass is not blocked. So your ball goes from here and it goes here. That means A and B are dependent. But if C is observed, then this pass is blocked. So you throw the ball here, just bounce back. So it's blocked. Then you can say, okay, A and B are independent given C, right? So let's look at another second basic case. It's called head to tail. So again, we look at how the edges meet at the nodes which are conditioned on C, right? So this is a head, and this is tail. So that's why it's called head to tail. So for the head to tail case, we still have like similar conclusion. Again, if C is not observed, conditional nothing, A and B are usually not independent. But if it's conditional C, we can safely conclude that A and B are independent. And we can verify this again. It's just mechanical. So the joint probability P of A and B and C can be written as P of A, right? And P of C given A and P of B given C, according to the structure. Now, if we want to check whether A and B are marginally independent of each other, we need to look into the joint probability of A and B, right? So this can be derived by marginalizing out C in the joint probability, so which is P of A times P of C given A times P of B given C, and the integral integrate out C, right? So you can pull the P of A outside of the equation. This has nothing to do with C, right? So, but the issue is this P of C and P of B given C. P of C given A and P of B given C in DC. So this term actually couples A and B again. So in the first term, C appears in front of the conditional part. The second part, C appears in the conditional part. But when you do the integration, the cost is that you just couple this term together. So it must end up with this integral must be end up with some term which couples A and B. That means in general you cannot decompose it as say a term of A only and term of B only. That's why in general you cannot conclude you're marginally independent. But what about conditional independence? So we want to look at P of A and B given C, whether they can be decomposed as P of A given C and P of B given C, right? If this holds, then they can say, okay, this is a conditional independent. And then just check it. P of A and B given C is P A B C divided the P of C, right? So just substitute this factorization for the joint probability. You end up with P of A times P of C given A times P of B given C divided by P of B. P of C. So if we take a look at the first two terms and then divide it by P of C, what do you get? So P of A times P of C given A is the joint probability of A and C, right? And divided by the P of C, you end up with P of A given C, right? So we can say, okay, A can be reduced to a product of P of A given C and P of B given C. So this is what we want. So now we can claim, okay, given C, A and B are conditionally independent. In other words, if we use the analogy of the rolling a ball, so this is like a path, right? So if you do not observe C, you can safely throw this ball along this path to arrive at B, so they are dependent. But if C is observed, it appears as a stone or barrier that your ball bounces back, meaning that A and B are independent. So the second structure. And then we'll look at the third structure, which is quite weird. It's an odd structure. It's called head-to-head. Head-to-head. So why it's called head-to-head? Because the variable C, which are conditioned on, we have this two edge heads points to, right? So this head and this head. So that's why it's called head-to-head. But the conclusion on this basic structure is contradictory to the previous cases. So basically, from this structure, what we can conclude is that if C is not observed, then A and B are independent. If C is observed, then A and B are not independent. It's just different, right? How do we see this? Again, we need to use a joint probability. We can write it as a P of A, P of B, and P of C given A and B. We first want to check this, whether A and B are marginally independent to each other, right? So to look into this, we need to calculate the joint distribution of A and B, which is calculated by marginalizing out the joint probability of ABC. Right? So now, what can we get? So this is P of A, this is P of B, this is P of C, given A and B, and you integrate out C. What do you get? You move A out, you move B out, so it's just the conditional probability of C given A and B. You integrate out C, it's just 1, right? So you immediately arrive at the product P of A and P of B. So basically, it means that A and B are independent when they are conditioned on nothing. When C is not observed, it's fine. But what if C is observed? What can we say, right? So if C is observed, we will look at P of A and B given C, which is the joint probability over the marginal probability of C, right? So we just substitute this factorization for the joint probability. What can we say is that P of A, P of B, P of C, and P of C, right? So what can we observe? So if we want to get to the conclusion that they are conditionally independent, it must be represented as a factorization of two terms. One term only contains A and C. The other term only contains B and C, right? So anyway, A and B cannot be coupled, right? But right now, so first C has nothing to do with A and B. We can just throw it out. But the issue is that this conditional assume P of C given A and B, it couples A and B. And you cannot remove it unless you assume that they are factorized. But in general, you cannot assume they are factorized. So basically, because both A and B is staying in this conditional part in one term, they are coupled. That means in general, they cannot be factorized. The consequence is, in general, they are not conditional independent given C. So you see the point, right? And head-to-head structure also reflect a particular effect. It's called exponential away effect, which is kind of special to the Bayesian modeling, but to me it's kind of reasonable. So here's a practical example. So suppose I want to construct a Bayesian network. What it has three random variables, B, F, and G, which models your car. B represents the battery status. So B is 1, meaning that the battery is alive, is charged. B is 0 means that battery is dead. And F is your fuel tank status. F is 1, meaning that the fuel tank is full, and 0 means that fuel tank is empty. And G is the electrical gauge. Electrical gauge in G is 1, meaning that okay, your electrical gauge indicates that you have a fuel, you have like a full tank of fuel. And G is 0 means that, okay, it indicates your fuel tank is empty. But there's a difference, right? Because some electrical gauge, it could have some errors. Basically means that if G is 1, that does not necessarily mean that your actual fuel tank is empty, is full. Probably it's empty. And also battery influences your rate of your gauge, right? Imagine that if your battery is dead, then your gauge, very probably electrical gauge, very probably will give you wrong rate. So here's our Bayesian network to represent their relationship. So the joint probability will be the probability of the battery status times the probability of the fuel tank status and times the read of the gauge given the battery status and the actual fuel tank status. And here is the parameterization. So basically, it's that in prior, I assume like the battery is alive, this chance is 0.9. In most cases, just the battery is fine. And in most cases, your fuel tank is full. And then given your battery is alive, your fuel tank is full, the probability that your gauge rate is 0.8 means that you have a large chance to get the consistent rate with your actual fuel tank, right? And if the battery is alive, but the fuel tank is empty, but still get a small chance to get the rate showing that your tank is full. So this is the wrong rate, but you still have some chance to get such a rate. The chance is low as 0.2. And similarly, given the battery is dead, but the actual tank is 1. So when the battery is dead, it may severely affect your electrical gauge rate. So that means your rate is consistent with your tank. This chance is low, 0.2. And also, if both your battery is dead and your fuel tank is empty, then you still get like a full rate of your gauge. This chance is even lower than 0.1. Right? So generally, this parameterization sounds reasonable. And now we want to check whether the fuel tank status and the battery status are conditionally independent, given given the gauge rate. So to test this point, we can just calculate the conditional distribution, right? The conditional probability that F is the fuel tank is empty, given your gauge rate is empty. And then we compare this probability that your fuel tank is empty, given the gauge rate is 0, and given your battery is dead. If they are the same, what does it mean? It means that this battery status and your actual fuel tank status are conditionally independent, given the gauge rate, right? And we can calculate this. This is just a practice of the base rule. And turns out they're different, right? Means that, okay, they are not conditionally independent. This is also expect because this is a typical head-to-head structure. So given conditional on G, you cannot conclude that B and F are independent. But the interesting observation is that if you do not condition on the battery status, the probability is bigger. Once you condition on your battery status is dead, the probability that your fuel tank is empty is reduced to 0.111. Why? This effect is called explain-away effect. Why? Because if you do not know the status of the battery, right? So when the gauge rate is 0, means that okay, I read my gauge is 0, then I can infer my actual tank is empty. We have this chance, right? We have this probability. And so that means I can use it. I can use my 0 gauge to explain some actual empty tank with this probability. Right? But now, if I have some actual information, that is the battery is dead, then my power of explaining the actual empty tank is shrunk, right? Is reduced. Is reduced to 0.111. The reason is that the observation of dead battery deprives of some explanation power of 0 gauge rate. That's reasonable. Because you can imagine that now that my battery is dead, so I cannot trust my electrical gauge rate. Right? So even I have like 0 gauge rate, I don't believe it is strong proof showing that your actual fuel tank is empty. That's why it's called explain-away effect. Does it make sense? And this is also this head-to-head structure reflect. Any question?
Is there a way to add conditions and get a higher probability then? There's no way. Adding conditions will decrease probability based on that?
Oh, it just means like when add condition b equals to 0, but b equals to 1 is another story. But when add b equals to 0, you can say the significant decrease of the probability.
Right, but is there any chance that
no.
In any case we increase it?
If you take b equals to 1, yes, probably. But if you take b equals to 0, it must decrease. And you can see like almost all kind of same phenomenon using this kind of model structure. This is like universal to Bayesian model. And this effect is called explain-away effect. And some people view as like a default or defects of Bayesian model, and they want to work out a way like even add this conditional, this chance or this probability won't decrease. That's another story. But I just wanted to be aware of this effect.
Is there a formal definition to the explain-away effect?
This is the formula. This is actually a observation. It's kind of empirical observation. It's interested. It's associated with practical examples. For example, if I switch to another example, like modeling spacecraft on orbits, this is another story. And your choice of value will be equal to 0 or 1 is different. But when you observe the decrease of probability, it is conditional on different scenarios. For example, for another scenario might be like b equals to 1, and it decreases. But you can find out the associations, the rational why it decreases. For example, in our case, like I know when battery is dead, my evidence of zero gauge rate is not as reliable as before, right? But in other practical examples might be another story. For example, when b equals to 1, I may believe your evidence is not reliable.
But isn't that good in this situation? Like, don't we want to be less sure that the battery is actually dead? Because now we have so that the fuel gauge is actually 0. Right?
Yeah, that's the I mean, how you view this. To me, it's kind of reasonable, but in some applications, we do not want this to happen. I do not want explain a way effect to happen. And there are like a set of tricks to avoid this. So this separation, this head-to-head structure has a more general case. Basically, if not only like C is observed, I mean, even any of C's descendant is observed, we cannot conclude A and B are independent conditional. C is observed or any C of descendants observed. That's the general conclusion. So to see this, we can just write down this, right? You can just look at the conditional probability of A and B given some descendant of C. So if you write it down, it's the joint probability B and blah 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 D, and this part, this dot represents the path from C to its descendants, right? So we need to integrate out this part to get the marginal probability A and B and D, right? And then divided by the marginal probability of D. But issue is that when you integrate out, you'll find A and B are coupled in the conditional probability of C given A, B, right? And then C serves like X, right? Given C. This is a descendant. And then multiplying with the X2 given X. Continue until you like D given like Xn. So you see that C appears in here and appears in here. And X is here in the part before the conditional and appears in the conditional. And you continue, you see when you marginalize out all those C, X, X2, and until the variable before D, that is Xn, you still couple A and B together. There's no way like the dependency of A and B can escape. So they see what I say. Any question at this point? To take the simplest example, like you have a P of A and B and C and D. We need to integrate of C, right? So we know it is P of A, P of B, and P of C given A and B, and P of B given C, and integral of DC, right? So you can say A and B are coupled here, and C is coupled here. So we will integrate out C. It must be a term which couple A and B and D. So you can say there's no way like A and B can escape out, run into different terms. That's why, in general, as long as any descendants of C observed, A and B are not conditionally independent. So now, with these three basic cases, we want to ask if there is an efficient way to answer the question that for arbitrary three non-overlapping sets of random variables A and B and C, whether given C, A and B are conditionally independent. Right? So here's the algorithm. It's called deseparation algorithm or baseball algorithm. So basically, the first step in your Bayesian networks, you shape all the nodes in C. It's consistent with our custom to draw your Bayesian network, right? For any observed random variables, you just shape the nodes, right? And then we look at every path from any node in A and any node in B. So you might have many paths. Each path connects to one node in A and ends start with one node in A and ends at one node in B. Okay. And we just look into every node in this path. If we find one node such that the arrows on the path meet as head to tail or tail to tail, and this node happens to inside C, then we can claim that this path is blocked. And we look at the next path. This means this particular case that A and B are dependent is not possible. Or in other words, like imagine you want to throw a ball, you want to roll a ball to go down this path, and unfortunately it is blocked by some node in C. Then you give up this path and look at another path. Or if the arrows on the path meet head to head, but this node does not appear in C, and any of its node's descendants do not appear in C, then we can claim this path is blocked as well. And then we move to the next path and see whether I can find a way to roll my ball and does not bounce back. Does it make sense? Three cases, right? So if I could just look into every path, like any path, if you find a node such that the node is inside C, and also the path meets at this node pass head to tail or tail to tail, then this path is blocked. You move to the next path. Or you meet a node which does not appear in C, and all its descendants does not appear in C, and the edges are meet like head to head, then this path is blocked. And we move to the next path. If some paths break this, we just return A and B. Conditional C does not hold. If every path is blocked, then finally we can claim that A and B given C are conditionally independent hosts. So in summary, you just check every path, right? If you can find out the path that your ball can roll from a node in A and goes to the node in B, then you stop and claim that this conditional independency does not hold. But if you try all kinds of paths, and every path is blocked, and the ball bounces back, then finally you can state that this conditional independence holds. Is it clear? So basically, just check 3 cases repeatedly for all paths starting from one node in A and from another node in C. So if any node is not blocked, any path is not blocked, then you say, okay, they are dependent actually. Otherwise, if all the paths are blocked, then you can say, okay, this conditional dependence independent host. So the last minute, give you two examples to verify. So A is here, just one single node, and B is this node, and condition on C. So now, we want to see whether given C and B are independent or not. Following an algorithm, we should check the path, right? From every path from A to the B, so it's actually only one path. Right? But the issue is that we found a head-to-head case. We found the head-to-head case, right? And unfortunately, C is conditioned. And also, E is conditioned, and E's descendant C is conditioned, is observed. What does it mean? It means that this path is not blocked. Remember, it's a weird case, head-to-head case, that any of the node where the edges meet head-to-head, if it is observed, or any of its descendants observed, then this path is not blocked, meaning that the variables are dependent. And it is just this situation, right? That means this path is not blocked. Your ball can go over here, and go here, go here, go here. So that means A and B are dependent, given C. Right? And we can look at another example. If this is your A and this is your B, but now we condition on F here. Right? So we can look at the example. We can look at the path. There's only one path here. So what can we observe? So no, this is we observe that this is a tail-to-tail, right? And for tail-to-tail, if you have some node observed shaded, that means your path is blocked. Then we can safely conclude that this path, your ball cannot travel. The ball cannot travel here from here because there's a barrier here. You bounce back. So A and B are independent given C. So here you can safely claim that given C and B are independent. Someone asked, like, what if I'm shaded here? What will happen, right? So if given F and C, whether A and B are conditionally independent. Think of it. Yeah, given C and F, whether A and B are conditionally independent. Yes. Why? Yeah, it's still blocked, right? As long as you find one node that can block the path, this path is like you can ignore it. It blocked. Well, although here, if it is observed, okay, this is not blocked. Your ball can go here, go here, go here. But now you found F is observed. You blocked. You bounce back. So A and B are still conditionally independent. Okay, so let's continue on next month.